Hello, my name is Ribana Roscher. I'm a junior professor of remote sensing at the University of Bonn. And this presented work is a joint work with Bohn and Garcke, both also working at the University of Bonn, and Duarte working at the University of Massachusetts Amherst. And this talk is about how to face remote sensing challenges in the bio and geosciences with explainable machine learning. And I want to start with a statement. A lot of people are quite skeptical about machine learning, especially deep learning and neural networks, because they seem to be the prime example of being a black box model. But recently, there are some efforts to make deep learning and neural networks more understandable to humans. And quite often when we use machine learning models, there are a few chosen characteristics which are desirable. Very often these are efficiency and accuracy. And as an example, I want to show you here a work from my group in Bonn, where we proposed a framework to detect hundreds of grapevine berries in images. And in this work, we were focusing on detecting the berries in as accurately as possible, and also to do it with a very efficient framework. But sometimes this is not enough, and researchers are also interested in understanding why the framework made a specific decision. And for this, there are some characteristics of machine learning frameworks which can help us in understanding these frameworks in a better way. First of all, we have transparency. Transparency is when you have access to the model and model components, and sometimes also to the motivation why specific elements were chosen. Then there's interpretability and explainability. And when my colleagues and I realized when we worked on this topic, we realized there's no unique definition of explainability and no clear distinctions to the term interpretability. So we came up with definitions, and interpretability we see as to present some properties of a machine learning model in understandable terms to a human. And explainability is when we combine these interpretable entities with domain knowledge. And why do we distinguish between these two? So you can have one interpretation, but as soon as you change the application, you might come up with different explanations. That's why it's important to distinguish between these. And in our work, which I present here, is we had a look at typical challenges we are facing in remote sensing. Not only bio and geosciences, but this also applies to a lot of other sciences. So first of all, we all know is that our data is complex. So we have, for example, high dimensions. Then, because we cannot handle limited training data, so because we cannot do everything via photo interpretation, and very often we need experts to help us with the labeling process. So furthermore, many of the pre-trained neural networks are made for RGB images or for point clouds with man-made objects. And very often this happens that these networks are not suitable to be used in the bio and geosciences, so we need to train them from scratch. Training a network from scratch can be a tedious process. So if we understand the models in a better way, it's easier to train them and to tune them. And when we have a look at the output results, an important point is that the result does not necessarily mean it's useful from a scientific point of view. And so one thing which is good to have is that it is ensured that the result is scientifically consistent. To ensure this, informed machine learning or theory-guided machine learning can be used to integrate the prior knowledge which is already known to us. The other thing is to make the result more interpretable and explainable. If we understand the estimation in a better way, first of all, it's more reliable because we can, for example, compare the result with our prior knowledge, existing knowledge, and also it might be more useful for us. And in our paper, we state that explainable machine learning can help us to tackle these challenges. And for now, I want to have a look at one specific goal, which is to increase the scientific value of the result. And this can be done, for example, by increasing the reliability or the trust of the outcome. And as one example, I want to mention one work. There are a lot more in the paper, and this work I present here is it's also presented at this congress by my PhD student Jana Kierdorf. And in this work, we used heat mapping as interpretation tool to visualize where a network looks in an image to identify specific whales. So here you can see 4 flukes, whale flukes of the same whale. And the highlighted part in the image is where the network, on which part the network based its decision. And it turned out that there are some parts which are quite helpful for the identification when used by the network, and others are not. So this heat mapping, this interpretation tool, can be seen as an alternative reliability measure besides the score of the network. Another way to increase the scientific value is to derive novel scientific insights. That means the framework is able to propose new scientific hypotheses, which were unknown. These scientific hypotheses were unknown to us before, and they are worth to explore. And this may even be seen as the opposite to the goal to maximize accuracy, because we want a framework to point us to signals and patterns where we don't expect them. And this may also be associated with a low accuracy of the network. And in the last part, I want to point you to some directions which I think are worth to explore in the future. For this, I want to show you what my colleagues and I found when we scanned many works in this area. And we classified all these works into groups. I cannot go into detail, but what is important, so all these groups are defined by a different level of transparency, interpretability, and how domain knowledge is integrated in the whole process. And I want to point out 3 findings. And the first finding is very often domain knowledge is involved in this design process, but not so often as actual prior knowledge in order to ensure a scientifically consistent solution. So, for example, when we know we have spatial patterns, we use convolutional neural networks, but if we have specific information about the spatial patterns, it would be good to integrate them in the whole learning process. So it's good to combine informed machine learning with explainable machine learning. Second finding, we had the range and diversity of works that explain the model output by the input, such as the heat mapping, is higher in comparison to works that inherently design interpretable and explainable models. For example, when you are immediately able to explain and interpret single neurons in a network. And the last thing is, as I said before, many works use explainable machine learning to align the model with prior knowledge, but not so often to exploit explainable machine learning for novel scientific findings. However, it would be really cool, for example, if we could use explainable machine learning to help us to find new definitions. For example, at the moment, there's no definition for classes such as wilderness. So the question is, can we use derived interpretations to explain what specific classes are? So to sum up, I see a huge potential of explainable machine learning in any kind of sciences. However, the requirement is to work interdisciplinary. And I would like to see more people working at the interface of machine learning in some kind of application area. First of all, there are a lot of relevant questions which are not solved yet. And here I would just mention the Sustainable Development Goals from the UN, which involves a lot of data analysis. And second, much more machine learning knowledge and suitable methods are needed in the sciences to solve these tasks. And with this, I thank you for your attention, and if you have questions, I'm happy to answer.